We're continuing with part 3, now talking about how action potentials work. So here they're showing a hyperpolarization, which is an increase in the polarity of the membrane, or the magnitude of the membrane potential, and thus making it harder to fire an impulse because it's further away from threshold. So here we have threshold at negative 55 millivolts. Here's normal resting at minus 70. If you hyperpolarize the cell, you take it even more negative, further away from threshold, thus requiring more of a depolarization to reach threshold and fire the action potential than normal. So the body can make these types of accommodations all the time to deal with varying stimuli so that you don't respond to stimuli when it's not necessary to. So the example I use in class is one of right now, as you're sitting there, assuming that you have them on, do you feel your socks? And on a normal basis, you don't feel your socks, because otherwise you'd go throughout every day with information constantly going to your brain saying sock, 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 and you wouldn't be able to function properly. So you don't feel them until you sort of need to. Here we have a depolarization. Depolarization is due to sodium entering. That's inside a cell gets more positive, so it's less polar or depolarized, and thus now a smaller stimulus will be needed to reach threshold and thus fire the action potential. So these both together are actually what we call graded potential, because the strength of the stimulus will affect how much of the ions, sodium or potassium, get moved or across the membrane. They can be larger depolarizations or larger hyperpolarizations, or vice versa, smaller and smaller. And as a result, you can have varying degrees of whether you're going to fire a potential or not. You can have a stimulus that occurs, again, like your socks, that is there, but you don't fire an action potential, and thus your brain isn't aware of it, or you don't respond to it in that way. So any stimulus that's strong enough to produce a depolarization that reaches threshold, negative 55, is going to produce an action potential. Now, action potentials are all or none. Once it hits this threshold level, there's no turning back. Sodium channel after sodium channel down the length of the axon fire, boom, 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 bringing sodium into the cell. This is why the line is getting more positive, until it reaches about positive 30. And at positive 30, this is the point at which sodium has reached equilibrium. That's the equilibrium potential for sodium. So no more is basically going in or out. You might have two going in, two going out, back and forth, this dynamic equilibrium, but we're at equilibrium. And at this point, all the sodium channels will close. So both voltage-gated sodium channels and voltage-gated potassium channels are involved. When a stimulus depolarizes the membrane initially, sodium channels are going to open, allowing sodium to diffuse. Now, these are not voltage-gated sodium channels. These are just sodium channels that respond to the stimulus itself. And there's a variety of different types of stimuli, both physical, like in pressure, or temperature, and so on. And then as the action potential, the peak subsides, the potassium channels are going to open. These are voltage-gated potassium channels. And potassium is going to flow out of the cell because there's a higher concentration in the cell than outside at rest. Once it flows outside, the potassium equilibrium potential causes a refractory period, or an undershoot, where the membrane potential of the cell goes below what it was at rest. It may go to negative 80 or negative 90, and as a result, during the refractory period, a second action potential cannot be initiated. It also cannot be initiated not only because the cell is so hyperpolarized, but also because the sodium and potassium ions are on the wrong sides of the cell. Remember, at rest, in order to fire, we need more sodium outside than inside, and more potassium inside than outside, so that they then go down their gradients. But during the refractory period, we have an equilibrium of those ions, equal amounts of sodium on both sides, and more importantly, equal amounts of potassium on both sides, and thus we don't fire a second action potential. So here you see the basic idea: sodium entering. Wait, where's number one? Resting state, nothing is happening. Everything is closed. Here we have a sodium channel, potassium channel, and then depolarization occurs. Sodium enters. Once sodium enters, this inside of the cell becomes more positive, and as a result, this triggers the neighboring sodium channel shown here to then also open and allow its sodium to enter. At the peak here, the sodium channels close. We've reached equilibrium. And now the potassium channels open. This is now in 4, and we have repolarization, potassium leaving the cell, making the cell more negative inside once again. And this continues all the way down until potassium reaches its equilibrium. And then we have to, here's the refractory period in 5, and then we have to even the ion concentrations out once again to get back to this resting state. And this is done with a sodium-potassium pump. An action potential can travel very long distances. In fact, you have one axon from the base of your spine all the way down to your big toe. That entire length is one axon, so they can be up on the order of feet, and it travels very, very quickly. And the action potential is constantly regenerating itself. As it's being sent behind the action potential, the cell is being reset. So here we have an action potential, sodium entering, making the cell more positive, and this travels down the line to the right, as you can see here. Repolarization is occurring behind, potassium leaving, making the inside negative again. And then following that, we'll have the refractory period and the sodium-potassium pump resetting the cell to its resting state there. Now, the speed of an action potential varies with the diameter of an axon. The bigger the axon, the faster the action potential. This is also tied to the amount of myelin wrapped around the cell. The more myelin that's wrapped around, the faster the action potential will be sent as well, up to a certain point. So here we have myelination shown down the length. These nodes of Ranvier, the signal is going to jump from node to node, essentially, and we call this saltatory conduction. In Spanish, saltar is to jump. And here you see only in regions where there is no myelination do you have ion exchange, sodium pumps and potassium pumps. So this is almost like the myelin is acting like insulation, preventing the ion channels from working. So any depolarization that's occurring in here signals the neighboring channels all the way down here to open. And of course, this can't be too far. There's an ideal distance that the node-to-node distance. But now this change in voltage is going to signal this node, these sodium voltage-gated channels, to also open and sodium to enter and continue the depolarization. And we'll pause here.